we consider this maximum likelihood estimation and maximum likelihood estimation method. So this is a method. Once again, you see that likelihood we have defined, likelihood of a particular, particular data. So it is basically likelihood of data given the model. That is the way we have considered the definition of likelihood. So here the models are represented by parameters. So maximum likelihood estimation is a method where you are trying to get that model which will be maximizing the probability of occurrence of data given those parameters. So this is how the likelihood estimation we consider. And here we assume that all your observations data, that means they are all following an independent and identically distributed identical distribution. And likelihood definitions we have already mentioned. So in the technical notations, you can see that likelihood of a parameter given data is expressed in this form. But essentially, so you will find more, this is more popular form of expressing likelihood of a parameter theta given data. But actually, what you are computing the probability of data given that parameter set, right? So this is the interpretation of likelihood with respect to parameter estimation that you need to understand. Now, if I expand this term by considering that property of independent and identical distribution for every observation. So this t is not raised to the power t. You understand this t is simply an index. T is a kind of instead of subscript, you have used superscript. That's all. It's simple superscript. It's nothing to do with raised to the power. So you should not be confused by this kind of representation. I have just followed Alpedine's representation. So you should understand in that way. So this is the product of all these probabilities. That means product of all the likelihood of individual data given that model, and then maximum likelihood of estimation of theta is actually the value of theta which maximizes this probability. Okay, so this is what we are going to determine that set of parameters theta which will be maximizing these probabilities. Now, one of the simplification in expression is that we can convert this, we can transform this expression in the logarithmic domain, because the nice property of log that it is monotonically increasing, and of course your argument has to be positive. So probabilities are all positive, so it could be 0 also, and that's a kind of very I mean, 0 means basically infinity. 0 means basically minus infinity in terms of logarithm. Anyway, so if you can handle that 0, so from the computational point of view, theoretically it is okay. So then it considers. So you are taking the logarithms of this expression. The advantage is that the product terms become summation, and the operations looks like linear operations. So once you get a summation, then the advantage that everything becomes something like a linear operation. So individually you can do, and all these things you can perform. So this is a simplified expression. So the same thing, like MLE of theta is once again the maximization. This estimate can be obtained by maximizing this log likelihood also. Now let us consider some of the distributions which we have discussed earlier. So one of these distribution is this Bernoulli distribution. And you know that a Bernoulli distribution, it's very simple in that respect that in this case, we consider a random variable which has only two possible outcomes, and that outcomes also are identified by the value of x is either 0 or 1. So it is basically the Boolean conditions of a random variable is expressing in a numeric form, and it is convenient to express also with these values. But this is how the mathematical treatment is also is taken. We carry out the mathematical treatment, use arithmetic operations, etc., using this value. There is no issue in that respect. So here the parameter p means it is probability of x equals 1. That is the definition of the parameters. And naturally, since there are two possible outcomes, so you have the probability of 0, x equal to 0 should be 1 minus p. And we know that if we consider that a data, if you consider a data here, probability of variable x. So x is a random variable, a particular data. So x could be either 0 or 1. Then the probability distribution, probability form, general form of probability, it's a point function. It is discrete values, probability point functions. That can be also expressed in this form. This is also one advantage of having 0 and 1 with the random variable x. You can see that same information is captured in this generic form. That means you put x equal to 0, then you get the probability of x equal to 0. You put x equal to 1, you will get the probability of x equal to 1. Is it clear? Right? I hope this is very simple, but now you should notice that this is the way we are writing. And then if you use this distribution, and you know that you can use the standard definition of expectation and variance of x, and with simple mathematical manipulations you can prove. And we have discussed all these things earlier also. You can also go through any standard book of probability. Then you will find that expectation of this distribution is p, which is the same as the probability of x equal to 1. And the variance of the distribution is given by p into 1 minus p. So this is the meaning of the Bernoulli distribution. So now, if I give you a data, and data is always in the form of these two possible outcomes of 0 and 1, and then given the data, you are asked to estimate this parameter p. Now, that is the parameter estimation. So if I use a log likelihood estimation of the data, and if I consider individual observations of x superscript t, then you can see that you can write this expression in this form. Any doubt on this particular expression, the log likelihood expression? Given the parameter p, we can write this expression for the occurrence of the data, which is a sequence, which is a set of samples, or I can say sequence also, it doesn't matter, from first to nth sequence, and each one is expressed as the random variable. Each one is expressed by a random variable x superscript t, right? So simple extension. So now, if I do some more mathematical manipulation and algebraic manipulation, some question? Okay. So you can simply reduce it into this form, right? So which one is the variable in this case for the estimation of parameter in this expression? Which one is the variable? P is the variable, right? So what should I do for maximizing it? For maximizing this expression,
GDP.
Yeah, we have to differentiate this log likelihood with respect to p and equate it with 0, and then find out what is the value of p in terms of this observation set. Is it clear? That's what we will be doing. And you will be doing this, as you can see, and this is what is your final result. Please do it by yourselves, in your leisure time, and mathematics is pretty straightforward. And then you will find the estimate of this parameter p. It is actually the average of the sample values. Now, this is one trick, once again, that 0-1 trick, that is also conveniently used while it is basically counting the number of, this summation is nothing but it is counting the number of ones. Now, if you use any other discrete levels, it becomes only the frequency counts of that particular level. So that is the interpretation there. But in a nice mathematical form, you can always express in this way. So this is the estimate. Now, when you have some estimate, there are also we'll come to those things in subsequent lectures. Like, we need to understand that what is the variability of this estimate, considering different set of observations you may get from the same process. So what kind of variability is there? That we'll discuss subsequently. But one thing that you note, that finally the parameter p, which is actually also the expectation of x, is also this p is the sample average. So sample average is the corresponding estimates. Now, if we extend this concept for a multinomial density function, that means instead of considering two classes, we may have k number of classes. So we are saying here k mutually exclusive states may occur, and pi is the probability of occurrence of ith state. So in that case, we can express this probability of x. So it just indicator variable. Xi is an indicator variable. That means it can contain 1 or 0, but the constraint is that if I consider at any point, I mean, it should be either 1 or x. I mean, for any particular observation set, you have so many xi's values, but you will get one of them only 1, and rest of them will be 0. And then what is the probability that it is going to be 1? So we can express in general form. It is like this: pi to the power xi, I equal to 1 to 2. So that is the probability of x when you are considering the corresponding multidimensional representation of a particular observation. So x is observed by this, how many variables? X is observed by how many variables? Here, k mutually exclusive variables, right? Actually k variables. So k dimensional quantity. X is in the Bernoulli case, it is x is two-dimensional quantity actually, in that sense, if we consider the extension of that. But no, we have not. It's an implicit representation. So we did not really consider explicit representation. But here we are considering explicit. So that's what it is showing here, that x is an observation represented by a multidimensional feature vector, where each dimension is a random variable. In that sense, it can take either 0 or 1. The constraint is that one of them would be only 1. So simultaneously, two of them cannot be 1. That is the constraint you impose here. So the maximum likelihood estimate also can be shown that it is, once again, for each one, it is expressed in this fashion. So you consider individual dimensions and you find out what is the how many times it has occurred. So it is simply counting that how many times that particular state has occurred by this representation, and then you are finding out what is the fraction of times that state occurs. That is also the estimate of the parameter pi using maximum likelihood estimate method. Gaussian density function is another example where you have a continuous random variable. Earlier, we have considered only discrete cases of a random variable, discrete random variables. We have considered both single dimensional random variable and multi-dimensional random variable. Though in our single dimensional random variable, in the context of multi-dimensional, it is actually two-dimensional. Here in this case, we are considering an univariate random variable, and this is a familiar expression of the Gaussian distribution, as you can see, and we all know that expectation of this random variable is the parameter mu in that density function, and in the form of the density function, and sigma square denotes the variance of the random variable. Now, if I estimate the parameter mu from a set of observations, now this time the values of individual observation would be from the continuous domain. That means they are real numbers. They are not discrete values like 0 and 1. And but the expression remains the similar thing like Bernoulli also. That means the expectation of that distribution, that is the parameter, that is the interpretation of that parameter mu, that is once again it's the average of the samples. That is very interesting. Okay, it has an uniform framework, and whereas the variances can be estimated in this form. That means if you do that, it is a maximum likelihood estimate of parameters. Then variances are basically the variances of the data samples from their considering their mean of the data sample itself. So these are the estimates for parameter mu and sigma or sigma square. Now we would be discussing a few interesting aspects of these estimators that would give you a better understanding that how reliable and how robust is your estimation. Because as I said earlier also that in the context of machine learning, also in the context of this kind of pattern recognition techniques or statistical techniques, point observation should not be sufficient. Any point observation is not sufficient. It's statistically speaking. If I say that some accuracy measure, for example, the accuracy of this method is this, we say always like that, but actually that is not sufficient. What you need to do also, you need to estimate, you need to show that what is the probable range with certain probability, with certain confidence interval, what is with certain with certain probability, what is the confidence interval? What is the interval of that that measurement? We have discussed this earlier also. So this particularly this approach has to be followed if you are really going to do theoretically any particular analysis. You should not stop just by estimating your or measuring just a single value. Like what is the particulars like accuracy I told you. You should also consider the corresponding variations, corresponding variances of the particular measure. So here also we are trying to relate those quantities that when you are estimating a parameter, as you see that if you estimate it, you know a particular value. Now, on the average, that is the expected value, you can say. But given any particular experiment, it won't be exactly the same value, right? It would be varied. It will vary from that value. So, what would be the probable range of variation? That is what we are going to do. So, this representation, so D is the estimator of a parameter theta. So, D is a kind of function given the sample, it's a function, it estimates the parameter theta. And now this estimate itself is also a random variable, because at different different data points for different training examples from the same process with different set of examples, you get your measurements that would be different. That won't be exactly same. So we can say that that is also a random variable. It randomly varies, and it has certain probability distribution also, which means it has its expectation and it has its variances. So we would like to see that what is the expectation of that your estimator. What is the expectation of your estimator? So you have given some estimation. You have derived certain estimation expression or method, I should say, and now what is the expected value from that also? So that is what we would like to see. Now this is one particular very important measure of the reliability of an estimate, is that the value what you are estimating, how much it differs from the expected value. So that is called bias. So the ideal case should be the expected value itself should be the estimated expression. So your estimation should be such that the expected value of that estimated measure itself should be the same. So we'll come to that. So that is the ideal case. So we would like to have an unbiased estimator. That is desirable, that this bias should be 0. And the other one which we will be also considering, instead of calling it variances, we will call that mean squared error, because variance would be the deviations from the expected value of dxxl. But that is not our concern. Our direct concern is that what would be the, on the average, what would be the this error if suppose there is a bias, or even it is unbiased also. So on the average, what would be this deviation from the true value of the parameter, right? So this is interesting, the case, and so these are the two things. And variance of the estimators is defined as the expectation of, instead of theta, we'll be using expectation of the estimator d itself. So that is the computation in the variance. Now let us consider the sample mean of a set of observations. Say you are trying to get the mean of the observations, which means that in a random variable, the interpretation of mean on the experiments if you extend it in probabilistic sense, in the random variables, it is considered that the mean of that distribution is the expectation of that distribution. So the mean is very much related with the expectation of that random variable itself. But the computation of mean is well defined. So you have your observations, and if you say that they are all identically independently and identically distributed particularly, that means there is no bias in your sampling. So these are sampled observations. If there is no bias in your sampling and you are giving them uniform weightage to every observation, so sample mean is kind of trying to estimate that expectation itself of the random variable. Right. So so if I use the analytical results of probability theory, and particularly expectations, expectation is a linear operation. So in the probabilistic term, a linear combination, expectation of a linear combination is the linear combination of the expectation of the random variables. That's a very well-known results. And you can see that expectation of mean is also the expectation of the corresponding random variable. So here mu is the expectation of that random variable. So I have not mentioned that mu is basically expectation of the random variable x. So sample mean is an estimate, an unbiased estimate of the expectation of that random variable. Sample mean of the random variables, instances is so it's an unbiased estimate. Yeah, please.
Sir, the second mu you have written in the second line, EM.
Mm-hmm.
And what's that mu? Mu is the estimate of xt.
Mu is expectation of x. Let me use this. It is just half showing.
M is the sample mean.
Yeah, M is the sample mean. So mu is expectation of the random variable x. Okay. That is what is mu. So consider any random variable. Mu is expectation of x. And M is sample mean. That means you are sampling this random variable. You are observing the values of this random variable in an experimentation. So that's the sampling operation. So you are observing it, say, capital N times, right? It is assuming some values, and we have considered the values would be numeric values, so that you can perform these computations. You can add them. You can. Is it clear? Okay, so that's what I mentioned, that sample mean is an unbiased estimator of mu. And what about variance? Now, variance of mean also can be can be expressed, can be found in this manner. So this is also a very well-known result, because sample mean is expressed as a linear combination of this. So variance is also expressed as a linear combination of this. This is a very well-known results, and you can see that here there is a problem. It should be
N square.
N square. It should be N square, because here N sigma square by yeah, it should be N square, no? Variance of xt. Variance of xt should be.
Yes, sir. If individual one is sigma, n sigma, then it will be totally n square sigma square, no?
Huh? No. Individual one is variance of xt is sigma square, right? Where I'm getting confused. Something I'm just getting confused. Variance of xt is sigma square. I think in the expression I have written, I'm missing something.
Sir, here the denominator will be 1 by n square, because when we initially we put it as variance of summation of xt by n. So when we take out the n outside, it will become 1 by n square.
Right. You are right. You are right. Right. So variance of this one, huh? Sorry, I'm using the pen. Yes, you are very right. I'm just confused. So variance of this quantity, and naturally this quantity, this 1 by n, here it would be 1 by n square. The scale factor will be So individual xt by n, it would be 1 by n square into variance of xt, right? Is it clear now?
Yes, sir.
Right. Thank you very much. So this should be n square. I will be correcting it. This should be n square, and this is n square, and then it is sigma square by n. Okay, good. So variance of m is sigma square. So you see that now the interesting part is that if your variance is also getting reduced of that of the estimation of the sample estimation of that mu itself. That means your estimates they are, as n tends to infinity, the variance is also tending to 0. Now this kind of property is is also a very desirable property in the for the point of view of estimation. We call it as a consistent estimator of mu. Right. Now let us consider the other quantity. So we have considered sample mean, and we have computed its corresponding expectation and corresponding variances. So once again, can you tell me what is the expectation of sample mean? So what we computed, expectation of sample mean is expectation of sample mean is
mu
related to the simply the expectation of the random variable x, right? Is it clear? And the variance of sample mean so this is very general result. This is very general result. It is nothing to do with Gaussian, etc., etc. Very general result. Variance of sample mean is the variance of that random variable divided by n. So variability is reducing in that estimate. That is fine. So now we are considering the estimate of this sigma itself, sigma square, this variance itself, right? So there you can see that estimate, we have maximum likelihood estimate. This is the maximum likelihood estimate. I have mentioned that you can derive it also using maximum likelihood estimate based approach, that log likelihood should be maximized and for this estimate, and then you will get this expression. Now here you can see we are just once again reducing these expressions, that this numerator can be written in this form. I hope you agree, no? This is standard computational variances. Earlier there was 1 by n. So you know that what is the variance of a set of samples? It is basically mean of squares minus square of means, right? Is it clear? So that is what you are doing here. I mean, if I just reduce this expression, it is mean of squares minus square of means divided by n, both the term. So that is what you have written here, right? So now again that linear relationships can be expressed, because this is so we have to find out, of course, what is the expectation. Now you would like to find out what is the expectation of this sigma square estimate. What is the expectation of this? That is your objective here. So which means you have to compute expectation of this, also expectation of this. That means, sorry, you cannot see my pen. So expectation of this term and also expectation of this term, m square and xt square, and then you can get that expression. So this is what you get, as I was mentioning, that you would like to find out the expectation of your estimate s square, and then you need to find out this. Now, expectation of the square of the random variable, that can be related with the variance and expectation of x. So this is the mathematical expression once again. Is there any difficulty in understanding these expressions, this reduction, that how expectation of square of random variable is related with its variance and its corresponding expectation? Okay. So this reduces that individually, if I consider any particular random variable of observation, so its square expectation of its the square should be mu square plus sigma square, and whereas expectation of m square is given as mu square plus sigma square by n, the same methodology. Now m has become a random variable here. Its expectation is mu and its variance is sigma square by n. So the same expression, what you have shown, that is also applied here, and you can just simply use that result. So you substitute it in the numerator, and you get a very interesting observation. So what is this observation says? You just take some time to read this expression, numerator part. If you have any question, please tell me, or if there is any error, please tell me. Is this reduction fine? So this reduction is coming from this expression from here. Right? So you are replacing this term. This is accounting this, and this term is accounting this. And then use simple mathematical. But the observation here, you can see that your variance, your expectation of a square is not the exactly the variance of the random variable in the distribution. So it's scaled. So it is not an unbiased estimator. So to get an unbiased estimator, you need to do something very simple. So S square is not unbiased estimator. So the unbiased estimator is actually n by n minus 1 S square. Because if I estimate n by n minus 1 S square, it's simply it's scaled. Your estimator is scaled. Then you get sigma square. So this is your unbiased estimator. Instead of S square, we will be estimating n by n minus 1 S square. That means we'll be redefining our estimates expression. Just scale it by n minus 1. Effectively, it means that I am computing standard deviation, but instead of taking n samples, I am taking n minus 1 samples while averaging. A very familiar expression you will find in many books. And as n tends to n is very large, this difference is very small. So sometimes we just simply ignore it. We simply consider sample variance is the estimate of the variance of the distribution. Because if n is very large, quite large, and mostly in sample estimation, n is sufficiently large, and this difference is very small. So it is asymptotically unbiased in that sense. So we have discussed about the mean and variance of an estimator. But what is mean squared error of an estimator? D. Now this is the definition. This is the definition we mentioned earlier also. It is not the variance, right? Because for variance, this should have been expectation of D. Sorry, this should have been expectation of the estimated D itself. This instead of that is what is variance definition. So there is no reference. There is no. So theta is like a ground truth. You have the true value of the parameter, and how this how your estimate is deviating from the true value on the average, the square of that deviation. That is what is mean squared error deviation. Now, naturally, if you have your unbiased estimator, expectation of your estimator is the same theta itself. So then mean squared error of an estimator is nothing but the variance of that estimator. Do you agree? But for a biased estimator, this is not the same, right? For a biased estimator, it would be different. So that is what we are going to see here, a simple mathematical treatment that we can reduce this expression into this form. So you can see that I am trying to get the components of variances and also the difference from the expected value of the, or the bias, I should say the bias. I'm trying to take out these two things separately and trying to express this mean squared error estimation in terms of variances and biases. So you can see this is a expansion, and you know that. Let me ask you this part. What do you think about this? What should be this quantity? Expectation of D minus expectation of, what is the expected value of this one? It is a deviation from the mean.
So 0.
It should be 0, right? Very good. So this part is 0, which means I am just left with these two terms, and these two terms are very familiar now. This is, what is this? This one? What is this term? In terms of variance and bias, what is it?
Sir, bias.
No.
Mean of variance.
Oh, sorry, variance.
Bias is a difference from the true value of theta, right? So this is variance and this is square of the bias. So expectation of the square of the bias. So we get this to quantity that we say that the variance, that is what is variance, and the other one is the bias. So variance plus bias is square. So naturally, when the bias is, so it is not yet complete. I have taken this part here. I mean, that is equal to 0 that you have said. So this is what is the expression for mean squared error, and this is nicely, you know, this is a figure taken from this book, and it has nicely expressed by this figure that you can see here that if your true value of theta lies deviated, it's deviated from the expected value, so this introduces a bias. So your sum mean on the average, the square error from this true value would be the variance plus the square of the bias. So this is the kind of interpretations, and it's very nice to see this kind of relation. So if I say that for the estimation of the mean, from the estimation of the mean of the population distribution or expectation of the distribution, what should be the mean squared error of that estimator? If we find that no, it is basically estimator is the sample mean. So what should be the mean squared error in that case? What should be the mean squared error of the estimator of the sample mean as an estimate for the estimation of expectation of a distribution? It's an unbiased estimate.
For sample mean,
Sigma square by n.
It's yeah, that is okay. That is basically, it is variance. That is fine. It's variance of that estimate. Okay. So sigma square by n is also okay, because that is what is the amount of variance. So maybe so we will stop here today, And I hope you will enjoy your puja vacation, and then we'll meet once again in the next class on Wednesday. So this is all.